Transition metals are almost always acidic, and why that is that they undergo what's called hydrolysis. This is an example of a copper transition metal, copper 2+, and this copper is surrounded by waters, but what happens is another water comes in and it extracts one of the H pluses from one of the waters connected to the copper. So if you look right about here, there's a hydroxide. The water stole that H plus and relatively easy from the water to make just a hydroxide, and in the process then you end up with hydronium. And hydronium is an acid. This is why most transition metal solutions are slightly acidic. Aluminum does this too, which is amazing, but it's the transition metals mostly. So if I were to ask you if a solution, say, of, I don't know, cobalt 2+ in water was acidic, basic, or neutral, cobalt 2+ is usually going to be acidic. So just kind of FYI on that. You can actually find Ka values. Not all of these will probably be in our table, but you can find Kas, and if you have a Ka, it's very likely to be acidic. Will a 0.1 molar iron 3 chloride solution have a pH which is acidic, basic, or neutral? All right, well, again, big surprise, iron is a transition metal. And iron, the transition metal, will have a pH which is acidic. That's going to give you a pH which is less than 7. Now, I totally glossed over the chloride because, again, chloride is the conjugate of a strong acid, HCl. Chloride has no effect on the pH, but wow, the iron will. Iron will undergo this hydrolysis to make an acidic solution. We've been looking so far at what's called monoprotic acids. Monoprotic, mono is one, single proton acids, and these are by far the most common. So monoprotic acids would be things like HCl, HF, HNO2. They only have one H plus that's able to be ionized and be acidic. This means that they'll only have a single Ka value as well. However, there are quite a few what are called polyprotic acids. Polyprotic means there's at least 2 or more acidic hydrogens. And down there at the bottom, I have 2 examples. Sulfuric acid is H2SO4. Both of those H's are ionizable, so that means they're both acidic. And the next one is called arsenic acid. Arsenic acid is a triprotic acid. It has 3 acids, 3 H pluses, which can be ionized, so it can create a lot of acid if possible. And the polyprotic acids and the monoprotic acids can be strong or weak. So you can see HCl is a strong acid, while HF and HNO2 are weak. And down there in the bottom, technically H2SO4, the first acid, H plus especially, is incredibly strong. So that would be considered a strong acid. The H3ASO4 is more likely weak. So it can be weak or strong, it's hard to say, but they are going to have a different effect on your reactions. Here's a reaction that shows what happens with a triprotic phosphoric acid. Now, phosphoric acid is H3PO4. So, for example, H3PO4 reacts with water. It makes the dihydrogen phosphate ion, H2PO4-, and hydronium. So, the first Ka, which we'll call Ka1, products over reactants, would be hydronium times dihydrogen phosphate divided by the phosphoric acid, and this value comes out to be 7.2 times 10 to the minus 3. Don't include water because it's a liquid, etc., but this would be the first acidic hydrogen. But phosphoric acid has another acidic hydrogen. H2PO4- can also react with water to make hydrogen phosphate and hydronium as well. So again, remembering not to include water, Ka2, hydronium times the hydrogen phosphate divided by dihydrogen phosphate ion. Notice the Ka for this one though, 6.3 times 10 to the minus 8th. Now as the K values get smaller, you end up with more reactants than products. So the first Ka is bigger, you're going to have more hydronium. And the second Ka here is not as big, so you'll have less hydronium. But this crazy thing even goes on to have a third acidic hydrogen. This is Ka3. So it'll also have some kind of conjugate base, in this case phosphate, times the hydronium concentration divided by the acid hydrogen phosphate. Ignore the liquid water. 4.2 times 10 to the minus 13. So you see here what's happening to the Ks. The first K is the strongest, the second K is usually weaker, and the third K is quite a bit weaker. So usually what happens happens in calculations, chemists just focus on the first Ka because that's the only one that has like a lot of punch to it. But on the right conditions, you can get the second and even the third hydrogen to come out. Just kind of realize that it's possible. Here are more examples of different polyprotic acids. Oxalic acid has 2 acidic hydrogens, the one on the left and the one on the right there, and there's their Ka values. Sulfurous acid has 2 acids. Phosphoric acid we saw has 3. Arsenic acid we saw a little bit earlier has 3 acidic acids. Carbonic has 2. Hydrosulfuric acid actually has 2, although the second one is so weak people wonder if it's really an acid at all. But anyway, there are also what they call dibasic and tribasic systems. A dibasic system would have 2 hydroxides. A tribasic system would have 3 hydroxides. And that would be different, of course, from a monobasic system like sodium hydroxide, potassium hydroxide. Here's an example of a diprotic acid. It's actually ascorbic acid, vitamin C, and it's got a long formula, so I'm just going to abbreviate it H2ASC, all right, where the ASC is the ascorbic acid. It's a pretty long formula. But anyway, there's the Ka1 and the Ka2 values, and again, note that Ka2 is a lot smaller than Ka1. Well, we can calculate the pH of a 0.050 molar ascorbic acid solution using this information. And what we'll do is we'll first find the hydronium from Ka1. We'll then also figure out the hydronium from Ka2, and ideally we'll add them together to give the overall hydronium, and then minus log of that will give pH. Now, in all of these, 100 times K is going to be less than C. So hydronium really is just equal to the square root of the Ka we're looking at times the Ca, and I'll show you that here in a sec. You can find hydronium from Ka1, you can find hydronium from Ka2, add them up to find the pH. So for the first Ka, the first acid that comes off, Ka1 will be the products over reactants, like all equilibrium constants. Now notice on the bottom we have the diprotic version of ascorbic acid, H2ASC, and on the top you have the conjugate base, which is basically the same thing as the acid but without an H+. So it's HASC minus times hydronium, and that equals Ka1, which is 1.0 times 10 to the minus 5, which equals x times x divided by the concentration 0.050. So x here is going to equal the hydronium, but also notice here that x is going to equal the concentration of the conjugate base, and that'll be important to us here in a second. So square root Ka times Ca, you end up getting the hydronium, 7.1 times 10 to the minus 4. Now, the second one, we have to be a little tricky because the hydronium from the second part is going to be the hydronium from the HASC minus, all right? It's already lost one H for Ka1. We're dealing with the hydronium from the HASC minus, the second one, and that's going to equal the square root of this new conjugate times Ka2. So notice here that we're using the same hydronium value from the first one, 7.1 times 10 to the minus 4, because that equals not only the hydronium, but it also equals the concentration of the conjugate base, which is the acid now in this part. Whoa, kind of crazy. But anyway, if you realize that, then square root Ka times Ca, the new Ka is 5 times 10 to the minus 12. The new concentration of the acid now is 7.1 times 10 to the minus 4. Throw this in your calculator. Hydronium, 6 times 10 to the minus 8 moles per liter. So the best way then to find the total hydronium and to find the pH then would be to add those two numbers up. So you want to add up the hydronium from the first one, 7.1 times 10 to the minus 4, and add it to 6 times 10 to the minus 8th molar for the second one. Now, with sig figs, you have to cut it off at the largest doubtful digit. And in this problem, when you're adding, that's going to be the 0.1 times 10 to the minus 4. And notice that the other number doesn't even begin until 10 to the minus 8th. So what this means is adding those numbers together, we don't have the sig figs to call it more than 7.1 times 10 to the minus 4. We have no confidence in the numbers to the right of the 7.1 and 7.1 times 10 to the minus 4. So hydronium basically equals the first hydronium from the first part, pH minus log the hydronium from from the first part, 3.15. The second acidic hydrogen didn't contribute anything to the pH. It was so small relative to the first one, it's almost like not interacting at all. And this is what we see most of the time with these polyprotic acids. Usually the second acidic hydrogen doesn't contribute anything to the first one. It's so small. If you just focus on the first one, you should be good to go.